Cool. So I've started recording. Let's um, let's do a bit of a recap. So last time we did like operators, right? So let's start from the very beginning. I'll just like move everything out of the screen. Um, yeah. So let's start with what propositional logic is. So what do you think propositional logic is?
So propositional logic is got two words in there. Logic is the study of arguments,
Mm-hmm.
and propositional means propositions.
Mm-hmm.
So using phrases which take on a truth value to sentences and connecting them.
Yeah. And can you give me examples of statements or sentences that are not propositions?
So there's a few. It could be an exclamation such as "ouch,"
Mm-hmm.
a question such as "How are you?" What's your name? Commands as well, such as play, uh, uh, be quiet.
Mm-hmm.
These are imperatives.
Yeah.
So these all don't have a truth value,
Yeah.
and everything. Well, yeah.
Yeah.
Most other things would be a proposition. I'm sure there's others. There might be some other types of sentences or statements which are not propositions, but
Hmm. Yeah. I mean, yeah, I think that's good enough. Okay, then we went into operators. Like we talked about like so okay, what's an argument?
so an argument is a set of premises and a conclusion. That was the first
Mm-hmm.
um, our first definition, which we came across in lesson one.
Mm-hmm.
And so a set of premises and a conclusion. So a conclusion is just the last proposition in the argument,
Mm-hmm.
and then the premises are what lead up to the conclusion. Hopefully, logically, they lead up so that we can get a an argument, which is I'm not I can't remember the word. There's soundness of an argument, but
No,
I'm
no,
not sure
no.
if we
Let's not
covered.
get into that right now. We'll get there
Right.
eventually.
Yeah,
But yeah,
but
like
anyway,
yeah.
yeah, yeah. What was your question? What's an argument? So it's a set of premises and a conclusion. That was our first
Mm-hmm.
definition. Then we revised it a little bit,
Mm-hmm.
and then we said that it's a set of propositions such that at least one proposition is a premise
Mm-hmm.
and at least one is a conclusion. And it's also possible for the conclusion to be the same thing as a premise. Well, it's just the same.
Oh, yeah. Right, yeah. You could have the same proposition as a premise and as the conclusion. In some
Yeah.
yeah, and that would still be an argument. Yeah.
Yeah, I think I didn't say it correctly. I think I said that. Yeah, the premise and the conclusion is the same proposition. Yeah.
Yeah. Right. So okay, and then how like we could talk about like the structure of propositions. So you have some like okay, how do you build propositions?
So, are we gonna be talking about logical operators
Yeah.
or not? Yeah. So, propositions can be uh, built up using these logical operators, either unary or binary operators. But
Mm-hmm.
there's we have one unary operator, which is the negation.
Mm-hmm.
So, for example, if you have a proposition such as the car is red,
Mm-hmm.
if you add the negation, it will become the car is not red,
Yep.
and then the binary that we covered last time, if I remember correctly, it was a disjunction and a conjunction. We haven't moved on to any other binary operators, but unary operators they just they just operate with one proposition,
Mm-hmm.
whereas binary operators they can connect two well, only two propositions. You can use multiple binary operators in a sentence, but each binary operator connects two propositions.
Yeah.
And the first one we covered was the disjunction.
You
And
don't
so,
have to go like in an order. Um,
okay, but
yeah, you
but
can
yeah,
go
anyway,
by anyone that you like want to go by.
yeah, we've already talked about the negation.
Mm-hmm.
So yeah, you've got a few of the symbols there that one could use to represent the negation. So
Yeah.
the what did you say? The middle one is called a tilde, right?
Yeah, it's a tilde. Yeah.
Yeah, I don't know the names of the one on the left, on the right. Well, the one on the right is an exclamation mark,
Yeah,
but
the left one is just a not symbol, like a negation symbol.
yeah. So then moving on to the disjunction, which basically means or.
Mm-hmm.
So we started uh, drawing out the truth tables and the
Yes.
symbols which yeah the symbols which you sort of similar to a V or a bird. It looks like
Mm-hmm.
uh, and yeah, so it basically means or,
Mm-hmm.
and so if one of the two propositions either side of this disjunction
Mm-hmm.
is true, then the whole well the whole
Proposition.
yeah the whole proposition is true.
Yeah. And what's so you have like let's say you have P and Q. What are P and Q called in that disjunction?
So either side they're called disjunct or
Yeah.
atomic propositions.
Yeah. They are both atomic propositions, and each one of them is a disjunct.
Yeah.
Yeah.
So just yeah, the analogy gave us if we're building a
Yeah.
molecule or a compound, you know.
Yeah. Yeah. That's right. Okay. So what are the natural language motifs for disjunction?
So the natural language motifs that we had were 1 minute. So or could be one, or either.
Mm-hmm.
I'm not sure if we covered any other ones, but I think those two are the main,
Yeah.
or either.
Yeah. Cool. Then we go on to conjunction.
So conjunction is it basically means the and operator.
Mm-hmm.
So again, you have two propositions either side of the symbol, making one whole new proposition, and it's represented using a and or yeah like a hat sort of symbol or a
Mm-hmm.
dot.
Yeah.
And in this one, both propositions need to have uh, a positive, well, need to be true
Mm-hmm.
to for the whole proposition to be true. If one of them is false, the whole proposition is false. If
Yeah.
both of them are false, it's false. And yeah, these are the truth tables for people to see.
Yeah.
Uh, it can also be represented using binary code, you said. So
Yeah.
instead of T's, they can be represented using ones for the true values and zeros for the false, for the, yeah.
Yep. Okay. And the natural language motifs?
So it could be and, both, also, in addition,
Mm-hmm.
as well as.
Yep. That's all that we discussed. Cool. So we'll start with the next. Um, yeah, with the next one. So that will be something similar to the previous one. It's a um, so this is generally like not taught because basically you can represent um, this kind of operator with using other operators. um, but yeah, like I'm just like teaching this because this kind of operation comes in everyday communication quite a bit. So a lot of the time is when people are using or, they don't mean a disjunction. So there are actually two types of disjunction. The disjunction that we discussed over here is actually not just the disjunction, it's an inclusive disjunction. So it's an inclusive disjunction because it includes the case where both are true. You know, so when you say um, either I have a sandwich or I have a pizza, the proposition is true even when I have both pizza and sandwich, right? So it includes that word. But there is another type of disjunction which is called the exclusive disjunction, which people use quite a bit in day to day communication. Uh, and you'll see what I mean when I show you the truth table of the exclusive disjunction. Oh, wait. So the exclusive disjunction again, um, this is usually like a so it's a disjunction symbol, but it has a an underline. So that is one way of representing it. I am not very sure about the other symbols. There is this some symbol. Um, it's sort of like an X-Men logo. um, and then the other one, like if you want to type it on a keyboard, what you can just do is draw V and put two underscores like that. That's what I do. I'm not sure if that's like a standard way of writing it, but if I want to type an XOR on keyboard, I just like write a V and I put like two underscores before and after. Um, oh, this is also called the XOR operator. Let me just move that aside a little bit so that I can write XOR. Um, XOR. So that's how it's pronounced. It's called XOR. And yeah, so it's an exclusive disjunction. That's why it's called XOR, because exclusive and disjunction is OR. Uh, and what this is basically when you have a binary choice and not like either you are going to eat pizza or you're going to eat sandwich, in the sense that you can only choose one. Like if I'm a parent, and I'm giving my child like choices, I'm like, I'll either buy you a pizza or I'll buy you a sandwich. So when I say that, I don't actually mean that I'll buy them both pizza and sandwich. I mean I'll buy only one of them. So that's when an exclusive disjunction is more appropriate than an inclusive disjunction, because it doesn't, like, an inclusive disjunction in that case doesn't capture what I mean when I say either or. Um, so like the truth table for that will be, I'll just take this. I'll just take the disjunction table.
I generally mean the same thing when I say or. I mean one or the other, so it's
Yeah,
quite useful.
exactly. So yeah, and this is important because when like we have like internet conversations, debates, and stuff like that, we like like not specifying this is kind of not not being clear. Like if you don't specify what kind of operation you're using, you're not being clear. Um, so it's better to like specify whether you're using an exclusive disjunction or like an inclusive disjunction. So over here, the only difference in the truth table is what? What do you think?
So, uh, if if they're both true, then that becomes false.
Yes, that's all. Yeah, that's the only uh, change that you will see in the truth table. So when both are false, it's false. When both are true, it's false. But when exactly one, is true, then it is true. So you can write true uh, when exactly one disjunct is true. That's like a one line example, a one line explanation of what this is. Um, so yeah, and natural language motifs are basically like the same as an inclusive disjunction. So I'll just write. Um, so from now I'll just like write an NLM as an abbreviation for natural language motif. Um, Same as uh, disjunction. A good practice is to specify when you're using it.
So for the people listening, yeah, NLM, natural language motif, it just means how we say it when we're speaking, whether it's online or in person.
Yeah.
How this.
So whenever we are like talking in some like human language, like English or I don't know, Spanish or any language, we are talking in like natural language, which deals with actual like sentences with meanings and stuff like that, not symbols. So when you're talking about symbols, you're talking more about you're using a formal language, but when you're talking about like the actual content of what those symbols represent, that's when you're talking about natural language. And natural language motifs are short phrases that appear in natural language to signify the usage of some logical operators. Um
Makes sense.
yeah. So I'm just writing this symbolically. So it's good practice to specify inclusive disjunction versus exclusive disjunction. Okay.
Yeah.
Um, okay. So that's it for exclusive disjunction. Then we'll go ahead and talk about probably one of the most important, probably the most important um, logical operator, which is the material conditional. The material conditional. And this operator is, you know, like also called the if then operator. Um, and it is represented with a bunch of symbols. You can use a right facing arrow. You can use a hyphen and a greater than sign, because like you don't have that on your like um, on your computer keyboard. On Android, like Google keyboards, you actually have access to this symbol. You need to go to the symbol section, and there is an upward facing, like to the power symbol. You just hold that and you'll get like a right facing arrow symbol. So you can get that on your mobile phones, but not on keyboard. So when you're typing on like a computer keyboard or a laptop keyboard, you could just use like a hyphen and a greater than sign. Although, yeah, it sort of looks ugly after some point. Um, you can also use a symbol like this, like a horseshoe symbol, a right facing horseshoe symbol. And a lot of logic textbooks actually use this symbol um, instead of this. But a lot of logic symbols use the implication like the conditional symbol as well. So these are like the main symbols. there are variations of this symbol, like a double, uh, you know, sort of like an equal to sign and a greater than sign. So yeah, like you can use any variation that you want. um, I just use the I just use whatever is available to me. um, Although I think this looks a little bit better, just like aesthetically. um, so yeah, these are the three symbols that we use mainly to represent a material conditional. And the material conditional is sort of it's very like it's easy to misunderstand, because what people like this let's just talk about the truth table structure of this, so that like I can tell you why that like it's a bit confusing, um, and how we can avoid that confusion. So yeah, we have the truth table here. um, Let me just change colors. Yeah, so that's the truth table for the implication. So of course an implication is true when both of them are true. It's like, yeah, obviously true. An implication is false when p is q and true is sorry, q is false. An implication is true when p is true, so that's t. And an implication is also true when both of them are false. um, yeah, so this is the truth table for an implication. And the reason I say this is a bit confusing is because people sort of misunderstand the material conditional for a different kind of conditional. Like, the material conditional doesn't um, very well capture what we converse in natural language. So I'll just mention that here.
Yeah, this one seems a little bit harder.
Yeah, it is, and it's very important to understand this, this particular point, because I like there are a lot of mistakes that I see people make in debates, which is like sort of like a derivative of this um, common of. I'll just write if then. Okay, I'll give you an example. um, if my one second. Just a second. Yeah, if my door is open, I'll just write it a bit here. One second. If my door is open, then I am not human. Okay. Um,
Yeah.
if I were to present this proposition to you and I ask you, do you think this is true? Um, what would you say?
Well, I'll just say they're completely two unrelated things.
But is the proposition true or is it false?
If you just ask me in the daily life, I would just say that seems false or
Yeah.
yeah.
But what do you think this proposition is? Like I know, like generally when I ask this to people, people will be like, "That's completely false." But that's not how the material conditional works. In Because like when we are using the if then statement in daily life, what we do is that we um, ascribe that there is some relation between P and Q. Like for example, like some yeah, like some other relation, not there is a relation. The relation is the implication, but like not a logical relation, some other kind of relation. Um, so I'll just move this a little bit here, and I'll explain the structure of a conditional. So a structure is P implies Q. Okay, and this is where like this is the first sort of symbol which is not symmetric, and it's not symmetric because both of them are not like both of them are atomic proposition. Like this is an atomic proposition and this is an atomic proposition, and this is a logical operator, but they have different names. Like this is called the antecedent.
Antecedent.
Yeah, and this is called the consequent. Okay, and this is really like you, I think you should remember these names, like the antecedent and the consequent. Like you can probably take some hint from the names, like like ante in Latin usually means like before. Like when you have for example, there are phrases in Latin like ex ante, uh, where ante just means prior, you know. And here it's the same thing, like antecedent is means prior or before, um, and consequent sort of like it means like after. So you visualize this as this is before, this is after, so that's why this is called antecedent and this is the consequent. Okay, so that's just like a structure of the material implication. All material implications have an antecedent and a consequent connected with a conditional symbol like an arrow. And yeah, so now I can be more like now I can be more elaborate about this. Like so over here, whenever we are evaluating the truth value of a conditional, we like let's just not talk about whether these two are like they are kind of interrelated or whatever. All we need to do is examine the truth value of this proposition, examine the truth value of this proposition, and then run it through the truth table. So in this case, my door is open, no, my door is closed, so this is false. I'll just like ignore these like other things. I'll ignore the natural language. I'll just see, okay, this is the first proposition, this is the antecedent, my door is open is the antecedent, I'm not human is the consequent. So the antecedent is false. I'm not human, that's also false, the consequent is also false. I'll just run these two values by the truth table. I'll go directly to the row where the antecedent is false and the consequent is false, and I'll check out the corresponding truth value. So this proposition in propositional logic is actually true, which is very counterintuitive. Okay, but this is like very important to understand. Um, so we also have some non-classical logics. Uh, like I'll just relevance logic. So relevance logic is like a type of non-classical logic, which what it does is it adds constraints to capture what we mean, um, like when we what we mean by if then statements in natural language. So typically in relevance logic, this proposition might not be true, um, because it's not clear that there is any relevance of of the antecedent. Like there's no relation apart from like the logical relation between my door and me being human, right? So relevance logic actually like it sort of puts uh, it puts constraints on what kinds of conditional statements are true, and that's a whole different sort of ball game. We'll not get into that for now. um, but yeah, for everyday reasoning and stuff like that, we can simply use the material conditional as it is and it'll be fine. Like we just need to be mindful of the fact that in an argument, like whenever somebody presents an argument, we shouldn't be like, this proposition is false because they are not related. No, it could just be true. Because like yeah, the antecedent is false and the consequent is false, so this proposition actually is true. um, so yeah, another way of thinking, actually yeah, we'll get to that part later. Yeah, I don't want to should I talk about that now? No, I'll talk about it later. Screw it. um, yeah, anyway, so we have the material conditional. So let's talk about some NLMs. I'll just write NLM. Okay, what do you think are the NLMs for the conditional?
So the natural language motives, if then,
Yes. So I'll just write this more a little bit more expressively. So it has to be if P then Q. Okay. Yeah. Then what else do you think?
perhaps when when P subsequently Q.
Okay. Can you give me like a natural language example of like how that would look like?
Uh, I don't think it'll be very good English, to be honest.
You could say
Yeah, I
when.
don't think it will sound very good, to be honest.
Okay, we'll just
When
yeah get rid of it. We want to be good at English. um, yeah,
I guess when P then Q, that could work.
that could work. Yeah. Okay. Then this entails that. P entails
This-
Q.
okay, so then P results in Q.
Okay. You could also have. Okay, so I'll cover something which you might not guess, but that is important to understand the material conditional even more. Um, P is a um, sufficient horrible handwriting. Sufficient condition for Q. Okay. Then another one is Q is a necessary condition for P. These are like other ways of specifying a material conditional.
How about P is a requirement for
Yeah,
Q?
of course. Wait, Q is a requirement. Q is required for P. So that like yeah like um, sufficient and requirement are not the same thing. So something could be sufficient, but it could be not required. Like something could, like for example, um, 10 kilograms of rice would be sufficient for you, but it's not necessary for you. You know, um,
Mm.
you could you could do with 5 kilos, but that doesn't mean 10 is sufficient. 10 is not sufficient. 10 is still sufficient. 5 is also sufficient, but 10 is not necessary, but 5 is necessary, you know. So yeah, so like that's a distinction between like sufficient and necessary. So in this case, like something could be sufficient, like it could be um, enough to substantiate Q, but it might not be necessary for it. So P might be sufficient to establish Q, but it might not be necessary to establish Q. Like you could probably establish Q with T, if not for P. You know.
It's a yeah, it's very abstract, but I think I'm sort of getting what you're saying.
Yeah, it's a
So
yeah. I think like yeah, this is a bit more like like this section is a little more thought provoking, to so to speak. There are, I mean, this is like a like necessary, sufficient. These are also sort of like modal terms. Um, so that like that also is like dealt with in modal logic. Um, so for example, if I say P is a necessary proposition, um, it means that if P is false, then there is a contradiction. You know, stuff like that. We'll get there. Um, but I just wanted to give you like a gist of it. Anyway, I think yeah, like these are generally like I think you'll see if, like conditionals being used with these sort of um, natural language motifs. Um, is there anything else I wanted to say? Let me think.
sufficiency is still a little bit vague for me. Would, would you have a definition
Uh,
rather than through examples?
well, you could say sufficiency, like a proposition is sufficient for another proposition when the truth of the proposition means the truth of the other proposition. So you could just like just the definition of the p like just the definition of the implication itself is the definition of what a sufficiency is. So an implication is true when the antecedent is true and the consequent is true, or um, the antecedent is false and the consequent is true. Like all of these cases, um, you could say they are like a P is sufficient for Q. Like it's just a way to replace the implication. Like you don't even have to think about like this in this. You could also think like, um, if this is true, right? P, when I say this is true, What I mean is, if this is true, then this is true. Like, the truth of this is sufficient to establish the truth of this. In the sense that if this is true, then this is true.
So I think that's why I said P is a requirement for Q, because
Oh, no, because a required something is required is closer to it being necessary. Like, it might not be like P might not be required for Q, because Q could be substantiated by T. So even if P is false, like even if this is false in the sense that P is true and Q is not. Oh wait, let me put it in another way. Uh, like over here, this is sufficient to establish this, but it's not necessary. Like, even if I get rid of this, right, I'll still have this establishing this. You see what I mean?
yes.
Yeah. So it's not a requirement, but like it's sufficient. So something like, when you say something is a requirement, it's sort of like saying it's necessary. Like, you could say Q is a requirement for P. That would be better.
Yeah, I see what you're saying, because P, if P was a requirement, then if it was false, then Q would not be able to be true.
Yeah,
But
but in the truth table, we know that if the antecedent is false and the consequent is true, and the implication is true, then Q is true. Or if this is true, even then it is true. Like, yeah, if this was a requirement, then this wouldn't be true, but this is true, so it's not a requirement. Yeah,
yeah, I think I'm following along.
yeah. Okay, is there anything else that I wanted to think about? Hmm. Oh yeah. Uh, oh, forget it. We'll discuss that later. So quite a few things like I want to say, but like in the interest of not making everything like a sort of like a one pot stew, I want to make like a more elaborate recipe. Um, we'll discuss that later. What we'll discuss now is some um, operations that you can perform on the conditional. Um, so there are like three types of conditionals. Types is a very weird word. Like, I don't want to use this. Like, um, but I don't know how else to put it. Maybe you can suggest. But basically, there are like three ways a conditional can appear. So three ways apart from, you could say four ways. Let's say four ways because let's include the canon version. So the first one obviously is the P implies Q. This is the conditional. The second one is called the converse. So Q implies P. This is called the converse. Then there is the third one, which is the inverse. So that'll be not P implies not Q. That is the inverse. And then the fourth one is not Q implies not P. Sorry. And this is called the contrapositive. Okay, so this you might need to remember. Um, Basically, P implies Q. That is the conditional. Q implies P, where you just flip it, sort of like, on the y-axis. That is the converse. If you sort of flip it, such that like you flip it in the sense that you change the truth values, then you get the inverse. And if you do both, you change the truth values and you do a sort of like a y axis rotation, you get the contrapositive. So I should mention that uh, this one and this one are logically equivalent. And um, how do I I'll just draw a circle. This one and this one are logically equivalent. And when I say logically equivalent, what I mean is that when you draw the truth tables, they will basically have the same values. So let's draw the truth tables for this, just to like show you, um, and then I guess we can wrap it up for today. And or yeah, we'll wrap it up for today after that. Okay. Okay. So I'm just drawing like a truth table. I'll just get rid of this. Okay, how about we start getting you to draw the truth table so that you also get into the practice. Um, well, okay, let's start with this. What would be the? I guess you can. I mean, we can do one of two things. Either you can tell me what to draw here, and I'll draw, or you can draw it and show it to me on camera or something like that. Hello.
Yeah. Can you hear me?
Yep, I can hear you.
Yeah, the first option was just that I tell you, right?
Yeah, you can tell me, and I'll fill out the tables. The other one is you draw and you show me. Which one would you like to do?
I think the first option for now.
Okay.
Yeah. Next
Yeah.
time I guess I can show you on a piece of paper or something like this.
Yeah. Cool.
But
So what would this be? Like, help me fill out this table.
so this is
Just the regular implication?
so this is just the conditional we were doing before, right? The same.
Yes.
So we got two truths, so it's a true,
Yeah. Okay.
and then a false and two truths.
Okay. Cool. Let's do the second one, which is the converse. And what is the converse? Like
So
what?
the converse, it's Q then P.
Yes. So I'll
So,
just.
so I'm guessing
Okay. What would this be?
that would be a false.
Wait. Why would it be false?
I thought it was just going to be the opposite of what was in
No, no, no,
the.
no. Just look at the truth tables and then pass them through the like to like yeah like when both are true is the conditional true.
Then yes,
Okay. What about this?
then false.
Wait.
So true.
Why would that be false?
Okay, I see what's happening. So the comes first. So then,
Yes.
okay, so then that will be so we got a false, then a true. So then that's a true.
Okay. What about this?
So then here we have a false and then a true.
Yes. So that's the second one. This is the conditional. This is the converse. Then we have, let's say, the inverse. I'll move it down later. Or I'll just move it. Sorry, just a sec. Yeah. Okay. What will be the inverse?
So the inverse would be not P then leads to not Q.
Yeah. So this, you will have to expand the table a little bit because yeah, you will need more columns. So yeah, I think it's a good time to start with how to draw like a truth table. So the first thing you do is declare all the variables. So you have P, you have Q, then you have not P, and you have not Q. Okay. And then what you do is you, one sec. You have not P implies not Q, right?
Yes.
Okay, so I'll just make the table. Just give me a sec.
Yeah, I wasn't expecting that, so I'm running out of paper on the side.
Oh yeah. Okay. So what would this be?
So then this column just it picks the opposite. So false, false, true, true.
Okay. What about this?
So same again, but the opposite for Q. So false, true, false, true.
Okay. Now you just apply the rules of the conditional and tell me what's the truth value for this one.
So here we have true,
Okay.
and then here we have a true,
Mm-hmm.
and then a false,
Mm-hmm.
and then a true.
Yes. Okay. And then we have the fourth one. I'll just copy paste this table because this one is also going to be as big as the third one. Then we'll modify it. And what's the fourth type?
The
The fourth type is called? I can't hear you.
contrapositive.
Yes. I'll just write contra plus V for contrapositive. I'll erase this. And this will be, what's the form of the contrapositive?
Not Q leads to not P.
Not.
So not Q implies not P.
Okay. And what will be the truth values?
So false, so not Q, false to false leads to a true.
Okay.
And then here we have a true and then a false. So a false.
Okay.
And then false and then a true. So a true. And then two trues. So a true.
Okay. Now notice this. TFTT, TFTT. You see that?
Yeah,
This,
so it's the
yeah,
their equivalent
yeah,
as we labeled with the stars earlier on, and then
yes, exactly. So these two are the same truths, same column basically. Logically equivalent. And this one are logically equivalent. Converse and inverse. Okay. So yeah, I guess that should be good enough for today.
yeah, that was unexpected. It got the level got a bit
Yeah,
higher.
a bit higher. Like yeah, but
I wasn't expecting.
yeah, I suspect this is like a small. I mean, not as well. I would say the level increase that you experienced here might not be as much as you go. Like this is like a significant jump. After that, like it'll probably be a little more um, linear. Like it'll be like it'll keep on increasing, but it won't be like as abrupt. But today was like really important. I spent a lot of time because this operator is the most sort of like misunderstood operator. People have a lot of problem with this. So yeah.
So just to recap so when both of them are yeah, it's got nothing to do with the actual meaning of the sentences. This operator is just to do with the true value of the two
Yes.
propositions either side, and then when when uh the second when the implication is true, it's always going to be true,
Yes.
regardless of what comes before it.
Yes. And one important point I want to mention is that all of these propositions can be sort of expressed in terms of other sorry yeah, all of these forms, like all of these operators, like the implication, or sorry, the conditional, or the disjunction, or the negation, all of these operators can be expressed um, in terms of other operators, and we will get to that like in some future session. But the idea is you can represent the conditional with a disjunction, or with a conjunction, or like a mixture of a conjunction and or yeah, you could have like a conjunction and um, a negation, something like that. Like a combination of logical operators can replace this operator. Okay, so we will talk about that later, and that's something you need to remember.
Looking forward to that.
Yep. Cool.
Yes.
So I'll end the recording now. Okay.